Dear students, in this lecture we are going to discuss how the integrated equation can be modified for gaseous phase reaction. Normally for gases we define these gases in terms of their partial pressure, but in most of the cases we have to replace the concentration of the reacting species in terms of the partial pressure of the gas. So let's see how we can modify this integrated equation as applicable to gas phase reaction. So let's take up an example, different gases here. We have a gas phase reaction which is of first order. So A gas reacts to give B gas plus C gas. Now condition being given at different time 0, time t and time infinity, partial pressure of the reactant A is given. At time 0, partial pressure is P naught. At time t, partial pressure is P P. So how we have to replace the concentration of A in terms of partial pressure? Now for this type of reactions, we have to assume the ideal behavior of these gases. Now assuming ideality of these reactants and products, so ideal gas, so we have pressure into volume is equals to nRT. So therefore, N by V is equals to pressure divided by RT. So N by V means the concentration of the reacting species, which is equals to pressure divided by RT, or we can say concentration is directly proportional to the partial pressure at a given temperature, because R is already a constant. So we have this concentration to be replaced in terms of partial pressure. Now for this reaction, the partial pressure of A at time 0 and at time is given as Pt. So using integrated equation of first order reaction, integrated equation as applicable to first law, we have this Kp is equal to 2.303 logarithm of the concentration of A initial divided by concentration of A left after time t. Now look at this. We have this concentration directly proportional to pressure. So initial A naught, partial pressure is P naught. So we can replace this concentration in terms of partial pressure P naught. So therefore, Kp is equals to 2.303 log P naught divided by Pt. So in this way we can replace concentration in terms of partial pressure. Now we can modify this in different ways. Take the second case, again using the same gas phase reaction, A gas converted into B gas plus C gas. Now for this reaction, the condition being given is at time, different times, time 0, t, infinity, total pressure, instead of giving pressure of A, we are giving total pressure. Total pressure of the system at different time. At 0 time, this is T naught. At certain time T, this is T. Now, from this, we have to derive this integrated equation. Now, for this, we have this A gas reacting to give you B gas and C gas. At time equals to 0 initial, let the partial pressure of A initial is P naught. So because when we start with this reaction A, there is no product P formation and product C formation. So the total the pressure at P equals to 0 should be the pressure of A only. So B will be 0, C will be 0 at time T. From this, some pressure has to decrease because as the reaction goes, amount of A decreases and amount of B as well as C will increase. So looking this equation, for every 1 mole of A that has been consumed, 1 mole of B as well as 3 moles of 1 mole of C will be formed. So therefore for every P that is decreased, there should be increase in pressure by P. What is P as well as P. So therefore look at this total pressure at time T. Total pressure at time T is equals to pressure of A plus pressure of B plus pressure of C. So this is equal to P naught plus P. So therefore this pressure decrease at time T. This is equals to total pressure minus initial pressure. So we have this. Now therefore look at this. We have to replace this concentration in terms of partial pressure. So partial pressure of A initial P equals to 0, that is directly proportional to P is equals to P naught, and partial pressure of A at time T, which is equals to P naught minus P. So we have this P naught, P is equals to Pt minus P naught, so minus Pt minus P naught, or equals to 2 times P naught minus Pt. So we have pressure of A at time 0, pressure of P at time T. So from this integrated equation we have At is equals to 2.303 log A naught by At. So this equals to 2.303 log A naught is P naught, At is Y is P naught minus Pt. So P naught is the initial pressure of the system at time 0. Pt is the total pressure of the system at time T. So we are replacing this concentration of A in terms of P naught and Pt. So this is another modification. Now let's see some other condition. Again we have this first order reaction, that is number 3. The conditions given is total pressure, that is pressure of A plus pressure of B plus pressure of C. Total pressure at time T, this is given as Pt, at infinity, this is given as P infinity. So total pressure of the system at time T and total pressure of the system at infinity. So we have to replace the concentration of A in terms of Pt and P infinity. Now again let's start in this way. At time equals to 0 initial, let the pressure of the system be P naught, that is the total pressure of A, because at this time there is no formation of B and C. At certain time T, from this some A reacts, so there is a decrease in pressure by some P. Along with this, there is a formation of 1 mole of B from 1 mole of A as well as 1 mole of C from 1 mole of A. So therefore, pressure due to B is P, pressure due to C is P again. At time infinity, at this infinity means we are assuming the reaction is almost complete. So at this case, the amount of A left is 0, so pressure due to A will be 0 and pressure due to B will be P infinity 0, due to C is also P 0. So this is the pressure of different system, method A, B as well as C at different time. Now condition says at time t, total pressure of the system is Pt. So therefore, at time t, total pressure of the system, that is Pt, which is equal to P naught minus P plus P plus P, which is equal to P naught minus, this will cancel out, this is P naught plus P. So therefore, P is equal to Pt minus P naught. P infinity, total pressure is P infinity. So P infinity is equal to P naught plus P naught. So this is equal to 2 times P naught. Now for this reaction, initial pressure P naught is not given, so we have to replace this P naught in terms of Pt and P infinity. So therefore, P naught is equal to half of P infinity. So we have this. Therefore, partial pressure of A at T equals to 0, that is P naught. So P naught is equal to P infinity by 2, and partial pressure of A at time T, this is equal to P naught minus P. So P naught is P infinity by 2, and Pt is, so P is Pt minus P naught. So Pt minus P naught is again P infinity by 2. So we have replaced this P naught in terms of P infinity. So this comes out to be P infinity minus Pt. So therefore, using integrated equation, we have Kt is equal to 2.303 log A naught. A naught is P naught. P naught is P infinity by 2, and Pt is P naught. So P infinity minus Pt minus Pt, or we can write in this way. So this is the case when the total pressure of the system at time t and time infinity is given. So this is the equation corresponding to the integrated rate equation. Now take another case. Again we have this type of equation. A gas gives you B gas and C gas. Now in this case, the condition given is, instead of total pressure, question says pressure of B and C is given. So pressure due to B and C. So at time t, this total pressure is T, and at infinity, this is P infinity. So in this case, total pressure is not given, but total pressure of B as well as C is given. So we have to replace this concentration of A in terms of B and C total pressure. So at time 0, we have P naught, this is 0, 0 as usual. At time t, we have P naught minus some P, so this is P, this is P. At t equals to infinity, this is 0, this is P naught, this is P naught. So therefore look at this, total pressure at P infinity, total pressure is P infinity. So this P infinity is equals to pressure of B plus pressure of C. So 2 P naught, or we say P naught is equals to P infinity by 2. At time t, total pressure due to B and C, this is Pp. So Pp is equals to pressure of B plus pressure of C. So this is P plus P, or P is equals to Pt by 2. So now we have to replace this partial pressure of A in terms of this P infinity and Pt. Now partial pressure of A at time t equals to 0, this is equals to P naught. So P naught is equals to P infinity by 2. Partial pressure of A at time t is equals to P naught minus P. So P naught is P infinity by 2. P is Pt by 2. So therefore from integrated equation we have Kt is equals to 2.303 log P naught. P naught is P infinity by 2 and Pt is P infinity minus Pt by 2. So therefore Kt is equals to 2.303 log of P infinity by P infinity minus P2. So this is the case when partial pressure of B and C is given. So we have this P naught is equals to P infinity by 2 and partial pressure of A at time t, that is P naught minus P. So P naught is P infinity by 2 and P is Pt by, so this is how. So this is the case. Now another case, let's see one more case here. Suppose we have this A gas reacts to give you B gas and C solid. And in this case, total pressure of B is given. At time t, this is Pt, and at infinity, this is P infinity. So as usual, at time 0, let this be P naught. This is 0. This is 0 because solid doesn't have any pressure. At time t, this is P naught minus P. So this is P, this is 0. At time infinity, this is 0. This is P naught. So therefore, at time t, total pressure is Pt. So Pt is equals to P naught. So this is P. Total pressure of B at time t is Pt, which is equals to P. At T equals to infinity, total pressure due to B is P infinity. So P infinity is equals to P naught. So we can replace this P naught in terms of P infinity and this P in terms of Pt. So therefore, partial pressure of A at T equals to 0, this is P naught. So P naught is equals to P infinity. Partial pressure of A at certain time t, this is P naught minus P. So P is equals to Pt. So this is equals to P infinity minus Pt. So therefore again from integrated equation we have Kt is equal to 2.303 log P naught. P naught is equals to P infinity and Pt is equals to P infinity minus Pt. So this is how we can modify this integrated equation as applicable to gas phase reaction. So simply saying the concentration of the reacting species has to be replaced in terms of the partial pressure of the reactant. So for this we have different cases. Now apart from this we have Let's see pseudo unimolecular reaction. Pseudo unimolecular reaction. Now this pseudo unimolecular reaction is also known as pseudo first order reaction. So the word pseudo means false. Though the reaction is not first order but it seems to be first order, and this reaction is not unimolecular but seems to be unimolecular. So we have certain reactions in which molecularity is not one but the reaction seems to be unimolecular, or we also have certain reactions in which the order of reaction is not first order but seems to be first order reaction. So these type of reaction in which the actual order of reaction is not one but seems to be first order reaction, these type of reactions are known as pseudo first order or pseudo unimolecular reactions. We have examples: hydrolysis of ester. So take this hydrolysis of ester. We have this RCOOR prime. This is ester. React with water in presence of acid as a catalyst. When this gives you acid plus alcohol. This is acid, this is alcohol. So actual rate law for this reaction is the rate is equals to rate constant K, concentration of ester. So with respect to ester, this is first order reaction, and the reaction also depends on the concentration of water. So this is a second order reaction. Rate depends on concentration of ester as well as concentration of water. So this is first order. So total order is 2. And if you look at this reaction, let this be the reaction, elementary reaction. So this elementary reaction, there is 2 molecules that is involved. So one is ester, the other one is water. So the molecularity of the reaction is 2. But in this reaction, water is taken as large excess, or the concentration of water is very high. So during this reaction, this water which is present in large excess, its concentration practically remains unchanged, or the quantity of water that is being consumed is negligible to the initial quantity. So since the water consumed is very small, so we can assume the water concentration is almost constant. So let this be equation 1. So since this being taken in larger excess, concentration remains constant, so we can merge with this rate constant K. So this reaction can be written as K prime into concentration of ester. So with respect to ester, this is first order. Let this be equation 2. What is K prime is equals to constant K into concentration of water. So solvent being taken in large excess, is concentration is very small amount reacted, so we can say that this is almost constant. So looking at this rate law, it seems that the reaction is first order. The reaction is independent of concentration of water, but in reality, reaction depends on the concentration of water. But the change due to change in concentration of water is negligible, so we merge with this constant K. So this equation is what we call as pseudo first order. Reaction seems to be first order, but actually this is second order. So in this equation 2, order of reaction, order is 1. This type of reaction is what we call as pseudo first order reaction. So let's see the union of this K and K prime. unit. We have this K prime and K. So K is equals to K prime divided by concentration of water. So K prime, this is pseudo first order reaction. So the unit of K prime should be time inverse divided by concentration. We have this. So therefore, unit of this K is concentration time inverse divided by concentration. So this time is measured in terms of second, concentration mole per liter. So mole per liter inverse second inverse, or we can say liter per mole per second. So looking at the unit of this, K is, since the reaction is second order, and this K prime is pseudo first order reaction, so is time inverse, which is equals to second. This is the unit of. Now this is pseudo first order kinetics. Now once we define this pseudo first order kinetics, so this equation being first order, integrated equation first order is applicable. So from equation to this 2.303 log concentration of A times 0 T is equals to K prime T, or from this we can define K prime. So K prime is 2.303 by T log A naught by AT. So once we define this K prime, from this K prime we can define the K, unit of K, or the value of K. So value of K is K prime divided by concentration of water. Therefore, K, the value of K will be equal to K prime. K prime is defined from this equation number 3, and the concentration of water is 55.56. So this is the value of K, chemical order of rate constant. This is pseudo first order rate constant, and this is how we apply integrated rate equation for a first order reaction. So this is pseudo first order reaction.